Okay. One last problem, which is based on the relation between Kp and Kc. Okay. All right. So this is the reaction. This is the equilibrium that we have. CaCO3, calcium carbonate का decomposition reaction. Solid is in equilibrium with calcium oxide solid plus CO2 gas. So the Kp for this reaction is given as 167 atmospheres, and this was calculated at temperature 1073 Kelvin. So you need to figure out what is Kc for this reaction.
Ma'am, can you give the value of R? I forgot.
Okay, not
Yeah,
a big
which
issue.
one to take?
So our atmospheres, right? So you can take R ka value as 0.0821 liters atmosphere per Kelvin mole. Taranum's already calculated it. Taranum, yes, absolutely. You got exactly right. Rest of you, are you stuck at calculating or where you at? Did you get the formula? Did you get the relation?
Stuck at calculating.
Okay. Maya, Sriti, Ansh, what about you guys? Where are you at? Okay, since it's been a while. So relation between Kp and Kc. Kp is equal to Kc into RT raised to the power delta n G. So basically it's the difference between the number of moles from products to reactants, right? So we know, okay, we're given Kp already here. Let's plug in the values. So 167 is equal to Kc is what we need to find out into R into T, 0.0821 into 1073 raised to the power delta n. So what is the value of delta n that you had to take?
Is it 1?
Correct. So how did you get 1?
Because delta Ng is basically products, number of moles of products minus the reactant.
Correct. So which would be the correct expression out of this? The first one or the second one? So delta N is 1. The value you get here is 1. But how would you arrive at 1? This way or
And
this way?
second.
Tarannum says second. What about the rest of you? Do you agree with her or disagree?
First, I think it's first.
Nah, it is the second one. Second is right. So the reason why we take delta Ng is we only need to consider the number of moles of gases alone. The reason is that for the calculation of Kp, solids don't exert, like they don't have any partial pressures associated with them, like they don't exert pressure in all the directions, right? So solids and liquids are not in consideration at all, like even aqueous conditions. In case of Kc, you need to like include concentrations, but when it comes to Kp, solids and liquids don't exert uh, like they don't have partial pressures associated with them. So in this conversion, whatever delta N you come across only deals with the number of moles of gases, which is why you come at delta N equal to 1, not because it is 2 minus 1, but because it is 1 mole of gas on RHS minus 0 moles of gas on the LHS. Okay, so that's like an important bit. That's why I had chosen this question. So whenever you're considering delta N, the reason why we call it delta Ng is because you only need to consider the difference in the number of moles of gases alone. Because only gases have any sort of bearing on Kp. Solids and liquids don't affect Kp all that much.
Oh, okay, ma'am, got it.
Okay. Cool. So once you've got these values, you just need to calculate it. Then Kc will be equal to 167 divided by 1073.
I'm getting like a big value.
You won't, because this is basically 1000 into this, right? So essentially it is 167 divided by 82 point something. Yeah, you
I'll
should
check
get,
my cal.
yeah,
Yeah.
you should get close to 2. What Tarannum got is absolutely right. So the answer you're supposed to get is 1.9. Yeah. Kc is in terms of concentration, so it would be mole per liter, 1.9 m. So this is the answer you're supposed to get. Okay. Miles, what happened? Like, where are you stuck? Did you get this value? Are you stuck at calculation? Where are you at?
Calculation only.
Okay. But otherwise, this is
Miss
the
had
formula.
messed up the calculation, but formula I got correct and
I
everything else
tried
is fine.
using. Tried not using a calculator. That's why I think.
इसलिए थोड़ा time. Okay. So that,
Yes.
yeah, with practice, you'll get used to it. That can do it. Okay. Awesome. So this is what we had covered yesterday. We had the basics of equilibrium and all the data related to it, you know, like equilibrium concentrations and what is the equilibrium constant, what if it's a gaseous reaction, all of these different cases. Units also, I just discussed that units of Kc or Kp depend on the reaction itself, because the expression, the formula itself changes depending on how many moles or molecules are taking part in the reaction. So based on that, the units keep changing. So applications of Kc and Kp, what are the different, like why do we need the values of Kp and Kc? Like why are we doing all of this analysis on, chemical reactions and equilibrium and all of that? How does it apply? So the first application, like the first use of equilibrium constant, is you can predict the extent of the reaction. So visually, you can't really figure out, like, okay, you can see that the like you have to keep checking the concentrations at different points. You have to keep checking, color also, like visually it's not very reliable factor, right? But we know that Kc or Kp, um, these are constants, they are equilibrium constant, and at any given temperature for a reaction, this is always a constant value. So if one person has already figured out what is the Kc of, say, decomposition of calcium carbonate at 560 degrees Celsius, then people don't need to do it again and again. You can just like refer this particular value for that temperature and figure out how much of the reaction would take place. You can predict the extent of the reaction. So how do you predict the extent? So you look at the value of Kc. Now it can be anything because it's literally ratio of concentration of reactants to products, right? So if it happens to be a really large value, so if you have a large value of Kc or Kp, something greater than 10 cube, what does it mean? Can you predict if you happen to have a large value of Kc?
That the reaction will happen and like proceed.
Reaction is proceeding because, yeah, equilibrium has been reached. But based on the based on the factor, like based on the value of Kc, what can you say about the reaction? I'll just write the formula here. So concentration of product upon concentration of the reactants. So large value of Kp or Kc,
Is it moving in the forward direction? Oh no, sorry.
it's
Oh,
it's
no.
equilibrium, no?
Yeah, sorry. No, what I meant to say is, I don't know why, but I think like the products will be more. So that
Correct.
means it will be on the extent of the reaction will be like a lot of products are formed and like there are reactants left.
Correct, exactly. So large value of Kc means greater products and lesser reactants. Only then the ratio is going to give you a large value, right? So this means that the products dominate in the reaction. If the products are dominating, concentration of products are a lot more, it means that the reaction has gone to almost completion. Almost, because there's a tiny amount of reactants left. Okay. Then alternative, on the flip side, if you come across a small value of Kc or Kp, so it's like less than 10 power minus 3, something like that, then what does it mean?
The exact opposite. That means
Yes.
products are less and reactants are more.
In this case, the reactants are dominating. So Kc can be less if the value of like the magnitude, the concentration of reactants is a lot and products is less. So this basically just means that reaction has hardly happened at all. So a tiny amount of products were formed and immediately the product started reacting to give back the reactants. Okay. So basically it just means that reaction has hardly happened. So based on the value of Kc and Kp, you can predict, okay, at which temperature is it ideal to conduct the reaction. So lower value of Kc, if you want more of the products, you don't want like, okay, you need to change the temperature. You shouldn't do the reaction at that particular temperature. Okay, so that is one application of equilibrium constant. You can predict the extent of the reaction. Based on that, you can take action. Next, another thing is you can predict the direction of the reaction. Okay, so in order to do this, there is a new term that's introduced. It is called reaction quotient. So reaction quotient is denoted by QC. It is literally, it's similar to what Kc and Kp represent, except it is not at equilibrium. Like reaction quotient, you can calculate at any point of time. So it's basically concentration of the products upon product of the concentration of the reactants.
Ma'am, but I have a doubt.
Yeah.
This means that the formula for QC is equal to Kc, right? So won't the value also be
Yeah,
equal
that's
to
what I'm
Kc?
saying. So Kc, like if you happen to calculate QC when the reaction has reached equilibrium, then QC will be equal to Kc. So that's how you can predict the direction of the reaction. So if you just happen to come across a reaction, like, okay, it's not like the reaction is happening in the wild. So let's say, like usually when in chemical factories and things, right, you need to keep track of the data values a lot. Okay, constantly at regular intervals, you need to figure out, oh, what is the temperature, what is the pressure. If something is going out of range, then you might be headed for a disaster, so you might need to take action. Okay, so all these different factors and variables are constantly getting recorded from time to time. So that way, one of such factors is reaction quotient QC. So which is literally, you can take it at the start of the reaction, you can take it at the end of the reaction. It solely depends on concentration of products upon concentration of the reactants. So if QC happens to be equal to Kc value for that particular reaction, it means that the reaction is in equilibrium. Okay. And if QC is greater than Kc, then what do you think will happen? In which direction will the reaction proceed in? So QC is similar to Kc in that the formula for both are the same, but Kc specifically is when the reaction is in equilibrium. That is why if QC happens to be equal to Kc, then the concentration of products and reactants are the equilibrium concentrations, and that's why you can say that reaction is at an equilibrium. If QC is greater than Kc, what does it mean?
Will it move in the backward direction?
Correct. And why do you think so? Like, why? How did you come to that conclusion?
I mean, random guessing. Sorry, but like
Okay.
it had to be another one, right?
So QC is greater than Kc means, what can you say about the concentration of the reactants or products compared to the equilibrium concentrations? Like greater, less? What can?
Greater than Kc, maybe.
Correct.
But like, okay.
QC greater than Kc means concentration of the product, like
Concentration
numerator.
is relatively high.
Yeah, higher than your equilibrium constant, which means that more amount of products are there in the reaction mixture than there are reactants. So for at that particular temperature, the products will start reacting to form the reaction, which means that the backward reaction is going to dominate. You're going to lose your products, and like, again, because concentration of products is more, the reaction is going to push towards equilibrium, so the backward reaction will be favored. And similarly, if you have QC less than KC, the concentration of products is lesser than the equilibrium constant, so this means that your forward reaction will be favored. Okay. So application of this particular factor is, let's say, you're working in some factory where you need to keep track. Okay, let's say it's manufacture of ammonia or manufacture of sulfuric acid, like all these chemicals that are important industrially and otherwise. You need to keep the forward reaction going because you want more yield, right? You want more product. That's the main aim of your business. So you keep checking on the concentration of the reactants and the products continuously in the reaction vessel. And if you want the forward reaction to keep going, all you need to do is ensure that QC is less than KC. Someone has already found out what KC is for that particular reaction. All you need to keep measuring QC and ensure that the value of QC is less than the value of KC. So as long as the magnitude of QC is less than KC, the forward reaction is going to proceed and you can keep producing the product. Okay. So that's kind of how the prediction works. And that way, yeah, like once you know the value of KC, you can use it. So based on this, you can, like, you want the reaction to, you want the maximum extent of reaction to take place, and you want the reaction to keep going. You don't want the reverse reaction to happen because you want to keep getting more and more product. So you can choose the temperature, ideal temperature for your reaction. You can keep ensuring that the reaction will take place based on your QC in comparison with KC. Okay. And another application of KC is, once you know what is the KC for a particular reaction, and let's say you're just doing some laboratory analysis or something, and you need to know what is the equilibrium concentration of the reactants or the products. So you can use KC to calculate what is the equilibrium concentration. Okay. So how do you calculate the equilibrium concentration is basically step 1, write the balanced equation.
Ma'am, just a second. So
Yeah.
these are the only two uses for equilibrium constants.
Yeah, basically applications, like practical application of equilibrium constant, 3 of them. So you can use the constant to predict the extent of reaction. You can use it to predict the direction of the reaction. Yeah, and you can use it to calculate equilibrium concentrations.
Okay. And one more doubt. So right now we calculated Kc, which is the So what happens when we're supposed to calculate like gases? Is it the same thing?
Yeah, Kc or Kp. So they represent the same values, just that the situations are different. If you are taking concentrations, then the value is called Kc. If you're taking into account, if you're doing your calculations
Partial.
based on partial pressures, then that's called Kp. That's it.
Okay, got it.
Okay. So how do you calculate what are the equilibrium concentration of either the reactants or the products? So basically you write the balanced equation. Second step you make this list. So you make a list of 1, what is the initial concentration that you've taken of the reactants basically. Second, what is the equilibrium concentration on going to equilibrium. So when the reaction has proceeded, so this is going to be like an unknown value. When the reaction has gone to equilibrium, what would be the equilibrium concentration? So on going to equilibrium, like as the reaction keeps proceeding, what is the concentration? How is it varying? And finally, once the reaction has reached equilibrium, what is the equilibrium concentration? Okay. So once you make a list of these at t equal to 0, at t equal to 50 seconds, at when t equal to the equilibrium time, just make like once you write the balanced equation based on the stoichiometric coefficients, you'll be able to write all of this. And you just substitute the values of equilibrium constant in the expression and you solve for the unknown values. So you know what is Kc, you know what are the initial concentrations, you know how much of it is left. So based on that, you can figure out how much of it is used up. So once you have your knowns and unknowns, you can solve for the unknown values. Okay. So we'll do a question related to this, like how this works. One moment. There you go. So let's say this is the question, okay? So this is the reaction that you're given. Production of nitrous oxide. N2 plus O2 gives 2N2O. So initially, let's say you're doing this reaction in a 10-liter vessel. You take 0.482 mole of N2 and 0.933 mole of O2. And you start the reaction. So some amount of NO2 has been produced. And you know that the Kc value for this equation is 2 into 10 to the power minus 37. Then what is the composition of equilibrium mixture? Okay, so this is the question that you have. How are you going to solve this? So since you know what is the value of Kc, you can use this to figure out what is the equilibrium concentration. So first step is write the balanced equation. So you're already given the equation. Let's write that. 2N2 plus O2 gives 2N2O. Okay. First step is, after writing the balanced equation, you need to make a list of initial concentration. So initial concentration at T equal to 0. What is the concentration of nitrogen gas that you would have? How much? What is the concentration of nitrogen that you took?
Second, the given concentrations that we have. Oh, they're not concentration; they're number of moles. Sorry.
Yeah.
I misread it.
But you can figure out the concentration from the given thing. So how would you calculate it?
Is it 4.82?
Taranam, you can multiply. So what is the expression for concentration? Molarity, how do you find out?
N by
0.0482.
Yeah. Okay. So concentration is nothing but N by V. So you know you took 0.482 moles in a 10-liter vessel. So this is going to be concentration of N2 at the beginning. Similarly, concentration of O2 is going to be 0.933 divided by 10. So what's a concentration of N2O at T equal to 0?
Zero.
Why do you think it's 0?
Ma'am, because at time 0, there should not be any products made.
Yeah,
right?
the reaction has not even begun yet. We
Correct.
can say that.
Yeah. So no products were made, so this is going to be 0. No reaction happened yet. Now reaction has started. Okay. By the time it reached equilibrium, let's say we don't know the concentration of the equilibrium mixture, right? Let's say X amount of N2 has reacted. Okay. So if X amount of N2 out of the 0.482 has reacted, how much of O2 would have reacted?
That should also be X only, right?
Will it be equal?
Okay, no. X by 2.
Very good. Stoichiometric coefficients. For
Yeah.
every 2 moles, yeah, you need 1 mole. So if X moles of N2 have reacted, then X by 2 moles of oxygen would have reacted. And how much of NO2 would have formed?
X.
X of NO2 would have formed. Correct. Okay. So if we are taking it in terms of the number of moles, then concentration will be X by 10, X by 2 into upon 10. So this is going to be 20 and it's going to be X by 10 again. N by V always. So at equilibrium, how much of N2 would be left?
Zero 0.482 minus X the whole divided by 10.
Correct. So it's literally what you took minus how much has reacted. So 0.482 minus X by 10. So similarly, you can figure out how much of what is the equilibrium concentration of oxygen by dividing these two, subtracting these two. And at equilibrium, if this much has formed, what is the concentration of N2 that is formed? So now you have initial concentration. You've got how much like ongoing to equilibrium, like what is the concentration that has reacted, and you've got your final at equilibrium, what are the concentrations. And you're also given what is Kc. So all you have to do is just apply it to the formula of Kc for this equation and solve for the unknown value. Okay.
Ma'am, are these the equations when they get like when they get like sort of complicated, we use quadratic equations in them in order to find?
Yeah. So you can use certain tricks. So the value of Kc is 10 raised to the power minus 37, right? Imagine 10 raised to the power minus 37, matlab it's going to be 0.0000, like you need 37 zeros and then you're going to get a 2. So this you can like literally equate it to approximately 0 itself. So that will basically kind of help you in your calculations also.
Oh, okay. Got
So
it.
keep an eye out for things like that. When you have extremely tiny values, you can neglect them. Try to what do you call? Yeah, try to approximate as much as you can, but within a certain range. If you approximate 0.047 to 0.0, like that doesn't make sense because 47 is still a value. Like what I'm trying to say is just even when you approximate, don't approximate to extremely simple values. It is just to make your calculation simpler. That's it. If you have 0.047, you can approximate it to 0.05 maybe to have simpler calculations. Okay. So that sort of thing. So yeah, you have your expression. Once you put it in the formula, solve for unknown values, and then finally, yeah, plug it in to find what is the concentration of equilibrium mixture. So that's another application of Kc. So when you calculate what is the concentration, if it happens to be equal to your theoretical value of your equilibrium mixture ka concentration, you can say that, oh yeah, now this reaction has reached equilibrium. That way. Okay. So yeah, so these are the different applications of yeah, your equilibrium constant. They help you in a lot of data analysis here. Okay. So now coming to Le Chatelier's principle. So what is Le Chatelier's principle?
It is a principle given by the scientist, French
Yes.
scientist, I would assume, and he basically gave conditions on how equilibrium shifts either to right or to like left when certain conditions are met, or like something like that.
Absolutely correct. So using Le Chatelier's principle, you can theoretically predict how the equilibrium is going to shift if you change any one particular parameter. Like if you change the pressure, what is going to happen? If you change one of the concentrations, what is going to happen? Okay. And Le Chatelier's principle states that the exact statement is a little like this, how it goes. It says factors affecting equilibrium conditions of the system is changed if any of the factors affecting equilibrium condition of the system is changed, then the system will move towards so what direction will it move? It moves towards reducing or nullifying the effect of the change. Okay. So this is what Le Chatelier's principle states. So the main thing you need to look out for is you need to see what factors are being changed, and then the system will move towards nullifying the effect of change. You need, like, you can predict it. So if you say that forward reaction, like it's going to favor the forward reaction, then see if that particular factor, whether it's temperature change or pressure change, is going to nullify the forward, like nullify that particular change or not. Okay. So let's look at like obviously there's only certain conditions that reactions have. So I'm just going to write it as a tabulated form, so you guys also can copy it that way, so it gets easier to uh, do the analysis like later on for reference and all of that. Also, it's pretty easy. So make 4 columns. Okay. So first we'll see what is the change. Based on that, how does the equilibrium shift? How does it affect the equilibrium constant? And if there's any special notes associated with it. Okay. So let's start with concentration of the reactants. If we increase the concentration of reactants, what direction do you think the equilibrium will shift in? So I'll just put the reaction here for reference. A plus B gives C plus D. So if I increase the concentration of the reactants, in which direction, like which reaction will be favored, the forward reaction or the backward reaction?
Ma'am, what are you're increasing concentration of the reactants only?
Yes.
Okay.
Concentration of the reactants.
Backward reaction will be favored. No, forward reaction will be favored. Sorry.
Yeah. So if we increase the concentration of the reactants, according to Le Chatelier's principle, we need to decrease the rate, the concentration of the reactants. Nullify karna hai na? So we are increasing it. So the reaction will try to decrease the concentration of the reactants. And in order to decrease the concentration of the reactants, should the forward reaction take place more or the reverse reaction take place more?
Forward reaction should take place more in an order to decrease the
Correct.
reactant.
So if we increase the concentration of reactants, the equilibrium shifts to the right. So forward reaction is favored. It moves in this direction. And anything will happen to the value of the equilibrium constant?
Will it be large?
No. So always remember, equilibrium constant is a constant. It does not depend on anything except the temperature. So equilibrium constant is not affected by anything except temperature. So the concentration of the products will get adjusted in order to ensure that Kc remains constant. That is why the equilibrium shift towards the right. So if you increase the concentration of the reactants, the concentration of products also will increase accordingly, so that the value of Kc will remain constant. That's the calculation. Okay. Next, similarly, okay, let's say we increase the concentration of the products. So this time I'm focusing on the products. I have increased the concentration of the products. Then what will happen to the equilibrium? Will it shift to the right or will it shift to the left?
Left.
Left.
Very good. Yes. So concentration of products increase kiya, so the reaction will try to decrease the concentration of products. It can do that if the reverse reaction takes place. So now the equilibrium will shift to the left. What is the effect on the equilibrium constant?
Nothing. Will remain the same.
Yes. Okay. Next, let's say I focus on the pressure. I increase the pressure of like one of the reaction conditions, I increase the pressure, then what will happen to the equilibrium? Forward reaction or backward reaction? So in this case, like I will give you guys a hint. There are two cases, okay? One, if there are gaseous reactants and products, and second cases, if there are no gaseous reactants and products.
Ma'am, I can tell you the first one because I've studied it before and I remember it.
Okay.
So in gaseous reactants and products, if the pressure is increased, the equilibrium will shift to the side which has less number of moles. So example, the right side has 3 and the left side has 2, then the reaction would shift to the left hand side if pressure is increased.
Correct.
I
Yes, absolutely right. One minor change, like a technical change I would do to what you had mentioned, is you need to look at the number of moles of gases. So equilibrium is going to shift where the number of moles of gases decreases. So basically, if you look at delta n, products minus reactants. So if delta n is less than 0, delta n less than 0, delta n negative means more number of gas molecules on the reactant side. If that is the case, then equilibrium shifts towards the right. And if delta n is greater than 0, matlab more number of gas on the product side, then the equilibrium is going to shift towards the left. Okay. So if like basically look at it this way, if there is an increase in pressure, you don't want to keep creating more gas because you want to reduce the pressure, right? Equilibrium is all about keeping that value constant. So you're going to shift the reaction on the side where you're producing less and less gases. So that's why equilibrium shift is where the number of moles of gases decreases. Similarly, if you decrease the pressure, then equilibrium will try to increase the pressure. So you can do that by increasing the number of moles of gases. So the shift is going to be where the number of moles of gases increases. It's going to be opposite of this.
and that is if pressure decreases. And we're
Correct.
just talking about the first case, right?
Yeah. Now, if there are no gaseous reactants and products, then what will happen to the pressure? Like what will happen to the reactants? So imagine a situation where you're doing a reaction in solution itself, like acid-base neutralization. Will that sort of a reaction depend on the pressure, external pressure?
Ma'am, can you repeat that?
Yeah. So I was just giving an example of a situation. So there's no gaseous reactant products, matlab you're doing the equation in solution itself. Okay. So the reactants, products, everything is within this solution itself. Now, do you think there'll be any effect if I increase or decrease the external pressure?
Yes, ma'am, there should be, right? Because the flask is open. The air pressure, the atmospheric pressure will increase, right?
Okay. Will that have any effect on reactants and products that are already inside here?
No.
No. Like there's no gaseous reactants or products, right? So all of the reactants products are in solution itself. Now, who cares what you're doing outside the solution? The reaction is only going to care if inside the solution the reaction conditions are different.
So it won't be affected.
Correct. Yeah. So if there are no gaseous reactants or products, then there is no effect, like, or almost like negligible effect for reactions in liquid solutions. You can say very little effect, almost negligible. Okay. So increase or decrease in pressure will only affect a reaction where there are gaseous reactants and products, reactants or products. If there's any gaseous species, then you need to look at, okay, in which direction is it going to, like nullify, like reduce the pressure. But if there's no gaseous reactant or gaseous product, there's no effect of pressure on the reaction at all. Next, okay, another thing, pressure change is not going to affect the equilibrium constant. Next, temperature. So if we increase the temperature, what will happen to the equilibrium? So in this case, again, it depends. Yeah.
Are there like two cases here for gaseous reactants and products?
So in temperature, again, it doesn't depend on, whether you have gas or not, but because it's temperature related to energy, right? So it depends on if it is an exothermic or an endothermic reaction.
Oh, okay.
Okay. So if it is an exothermic reaction, like can you, any of you attempt making a prediction? So exothermic reaction में क्या हो रहा है? Exothermic reaction में already a lot of heat energy in the form of heat or light is released. Now,
Oh,
yeah, if you increase the temperature, will it help in nullifying the change?
no,
Temperature?
so the reaction technically should move backwards because in an order to, yeah, as you said, nullify the change.
Yes, absolutely. So exothermic, you want to nullify the change. Energy is released, matlab, um, you don't want to add to more energy. So the equilibrium is going to shift to the left. The backward reaction is favored. And in the case of endothermic, what will happen?
Will shift to the right.
Correct. So endothermic mein, your energy is absorbed by the reaction itself. So the more you heat, like the more energy you give it by increasing the temperature, the more it will favor that reaction to take place. Like, oh yeah, give me energy, I'm gonna go ahead with the reaction. So endothermic, the forward reaction is favored, equilibrium shifts towards the right. And exothermic, increase of temperature is going to favor the backward reaction. So the equilibrium shifts to the left. What will happen to equilibrium constant? as temperature increases?
It will decrease.
Correct. So the value of equilibrium constant is going to decrease. So this is based on the formula that we discussed yesterday. So delta G equal to minus 2.303 RT into log K, right? So it's like a logarithmic relation. So overall, both of them are inversely proportional. As temperature increases, the value of K decreases. And another important part, again, another note that you can figure with this is that the equilibrium is usually achieved faster. Okay, so whether it's exothermic or endothermic, higher temperature usually means that the equilibrium is achieved faster. Something that's already there in equilibrium, if you increase the temperature, then it's going to shift based on whether it's an exothermic reaction or an endothermic reaction. Next, effect of a catalyst. So if you add catalyst, will it affect the equilibrium? Will the equilibrium shift in any direction? This is something we discussed yesterday. What will happen to the reaction on adding a catalyst?
Ma'am, does not affect.
Very good. So no change. Will it affect the value of equilibrium constant?
No, ma'am, that will also remain unaffected.
Correct. So again, just like with temperature increase, catalyst only ensures that the equilibrium is reached faster. It doesn't affect anything else of the equilibrium. Okay. And there's one more thing we need to discuss. What if we add an inert gas to a reaction that's already taking place? Okay. So are you guys noting this? Can I go to the next page, or do you need some time in noting this?
Ma'am, I finished noting it down.
Okay. All right, going to the next page then. So if the change is, if you're adding an inert gas, inert gas doesn't mean just any of the noble gases. It means that if you add any gas that has no effect on the reaction, like if it's a reaction between decomposition of calcium carbonate, for example. So you're just heating calcium carbonate and that decomposes to calcium oxide and carbon dioxide. So in the reaction vessel where you're doing this reaction, if you add nitrogen in the mixture, now calcium carbonate is not going to react with nitrogen. Calcium oxide is also not going to react with nitrogen. Carbon dioxide also is not going to react with nitrogen. Okay. So nitrogen, even though it's not exactly a noble gas, it's not an unreactive gas, but in that context, for that particular reaction, it is an inert gas because it's not going to react with anything in the reaction vessel. Okay. So adding an inert gas basically means that, like something that does not react with anything in the reaction mixture. So what happens if you add any inert gas? So two cases here. If you have a reaction vessel, right? If you're adding additional gas to it, either you can add it at constant pressure, or you can add it at a constant volume. Remember, PV equal to nRT, right? So you're not changing the temperature, you're changing N, which means that either V will change or P will change. Both can also change, but yeah, like in order to figure out which direction the equilibrium is going to shift, we're going to consider two cases. If you're adding at constant pressure, so the overall pressure in the reaction vessel is kept constant, which means that to accommodate this extra gas, you're increasing the volume of the reaction vessel. Okay. So if you're increasing the volume in order to add this inert gas, what are you doing to the pressure of the reaction itself?
Mom, I didn't get it.
Okay.
Like whatever you just said.
This is my reaction vessel. Or let me just start over. Okay. So this is my reaction vessel. So I have my reaction mixture here. Some reactants, products, there's like gases over here. Like if there's like gaseous reactants or products, then yeah, that particular gas is going to occupy this part. Okay. Now I'm adding some inert gas to this mixture at constant pressure. If I'm not changing the overall pressure inside the reaction vessel, and I have to add additional gas, I have to create more room for the gas to occupy, which means that I'm going to change the volume of the reaction vessel. Initially, it was till here. Instead, to accommodate the extra gas, I'm going to increase the volume of the reaction vessel and add the inert gas over here. Then what is going to happen to the overall pressure of the black color gas that is already there in the mixture? With respect to the black color dots that are already there, what happened to the overall volume?
It increased.
Which means that the partial pressure of the black color gas has increased or decreased?
Has increased.
If the volume increases, what will happen to the pressure?
Decrease.
Yeah. So the pressure with respect to the black color gas, which is a part of the reaction, has decreased. So basically, you're indirectly decreasing the pressure in the reaction vessel by adding an inert gas, by maintaining the overall total constant pressure. Okay. So if pressure with respect to the reactive gas has decreased, in which direction is the equilibrium going to shift? So this is going to shift in the direction, it's going to shift where the number of moles of gas increases.
Ma'am, I'm confused.
Yeah, I'll take an actual proper example and explain. So consider this reaction, okay? In a closed vessel, you're decomposing calcium carbonate, CaO plus CO2. So initially there was no gas. The only way gas will be produced in this reaction is if the forward reaction happens, like as more calcium carbonate decomposes, more CO2 is going to be produced. Okay, this is an equilibrium right now. Now you added an inert gas. Overall pressure needs to be constant, which means that if the overall number of moles of gas is increasing, the volume of the reaction vessel is increasing, which means that total available space that this CO2 can occupy has overall increased, right? So what happened to the partial pressure of CO2? Like if you consider only the reaction, what happened to the pressure of CO2? The pressure exerted by CO2 has increased or decreased?
Decreased.
Pressure decreased, right? Pressure exerted by CO2 has decreased. So now, if there is more space occupied by CO2, overall pressure has decreased. What did our change in pressure say? Like if overall pressure has decreased, how is the equilibrium going to shift? So if pressure increased, then the shift is where the number of moles of gas decreases. If pressure decreased, our equilibrium is going to shift in the other direction where the number of gas increases. So because there is more space for the CO2 to occupy, the equilibrium will want to maintain that constant pressure that was there initially with CO2. So it'll try to increase the pressure of CO2, and that can only happen if more of the reaction takes place. So the equilibrium shifts in the forward direction to produce more CO2 so that that initial pressure when it was in equilibrium can be maintained. Okay, better or
I'm still not able to.
not, still confused?
Because
Yeah.
what we were told were ki in inert gas, they do not affect the equilibrium, they do not affect the rate of reaction.
No, so that's why there's two different cases. If you add an inert gas at constant volume, if the volume remains constant, you're just adding an extra inert gas over here, then in that case, there is no effect. At constant volume, overall pressure will still remain the same with respect to whatever gases are there in the reaction. So in this case, there is no effect, there is no change.
When you
But,
say the volume is constant
sorry?
and we are adding a gas, when you say the volume is
Shouldn't the pressure increase? Because the number of atoms that exert pressure are increasing, right?
So the total number of atoms, the total pressure is going to increase. But the partial pressure with respect to CO2 alone is still going to be constant.
So the partial pressure will remain constant. However, the total pressure of the system will increase.
Yeah.
This is at constant volume, right?
Yeah.
Okay.
Okay. So if the volume is not constant, like if you're trying to keep the total pressure constant, it means that the volume is changing, which means that the pressure exerted, like because the space available for the gases involved in the reaction is changing, that's why the overall equilibrium is also going to shift. So if you're adding an inert gas, you need to check whether it's at constant pressure or at constant volume. If it's at constant volume, there's going to be no effect. But if it's at constant pressure, the volume is shifting, matlab you're doing the opposite of, whatever, like you're indirectly changing the pressure inside the reaction vessel. Pressure with respect to this particular this thing. Okay, so this is Le Chatelier's principle. So application of Le Chatelier's principle. So again, based on how you want the reaction, like which reaction you want to take place, you're going to adjust the reaction conditions that way. So for example, if you want more number of products to, like if you want the large quantity of products, you want the yield of the reaction to be nice, because then you're going to get more, can sell more. Then different ways of doing it, you can increase the concentration of reactants, so that's going to push it towards the right. You can decrease the concentration of products, so decreasing the concentration of products is going to push the reaction towards the right. So decrease the concentration of products means you need to keep constantly taking away the products from the reaction vessel, so that way the reaction can keep going in the forward direction. So if the reaction involves gases, then you can manipulate the pressure so that the forward reaction can take place. Then again, if it's an exothermic or endothermic reaction, then you can manipulate the temperature so that the forward reaction can take place. Like if it's an exothermic reaction, you will ensure that there is a coolant constantly circulating the reaction vessel, so that that coolant can keep decreasing the temperature. And if it's an endothermic reaction, then you can ensure that you're constantly supplying heat energy to the reaction vessel, so that the forward reaction is favored. Okay. So that is basically the application of Le Chatelier's principle. So depending on which reaction you want, you will keep manipulating the concentration of reactants, products, pressure, and temperature, whichever is easy, or a combination of all of them. Let's say, for example, it's holiday season, you want the yield to be minimal. Then you're going to increase the concentration of products so that equilibrium condition can be reached, and it's not going to lead to an explosion. Like as more products are formed, then they come back to form the reactants. Then you can come back and take away the products so that you can continue the reaction in the forward direction that way. So that's like the main application of Le Chatelier's principle. So these are the different factors you can manipulate from your side, so that you can control which direction and how much of the reaction will keep taking place. A lot of times, pressure is manipulated by the addition of inert gas. Either you have a piston system that changes the volume, or you keep like adding or taking away the gas in the reaction vessel that way. Okay. So the first part of the chapter is all done with this. After this, we have a whole lot of stuff about ionic equilibrium. Okay, so we have a little more than 15 minutes left. Do you want to do more problems and questions based on application of equilibrium constant itself? It's going to be very similar to the questions that we did at the beginning of the session. Or you want to start with ionic equilibrium now?
Can we start ionic equilibrium like fresh in the new lecture?
next class.
That
ठीक है.
yeah is next week only.
Okay, cool. That works. Yeah. So
Okay.
now we'll do some questions based on equilibrium constant then. Hmm. Okay, similar to calculating what is the equilibrium concentration of any particular reaction. So this is another question that I have. Okay. So let's say we have this reaction, nitric oxide plus bromine is in equilibrium with NOBr. Okay. So you take 0.087 mole of NO and 0.0437 mole of Br2. So they're mixed in a closed container at constant temperature. At equilibrium, you see that you've got 0.0518 mole of NOBr. Okay. Then, what are the compositions in the equilibrium mixture? So you know the composite, like the what do you call concentration of the product at equilibrium. You need to figure out what are the concentration of the reactants at equilibrium. Okay, so this is the question. Mind the composition of equilibrium mixture matlab what are the concentration of the different species during equilibrium of the reactants and the product. So I'll leave it to you guys, give it a try. After about 10 15 or not 10 15 minutes, after a couple of minutes or so, we'll see how to do it. You guys first put some thought into it, try to do it. Okay.
We need to find the concentration of each and all of these, no?
Yeah. So at equilibrium, you're already given concentration of the product. You just need to find out what are the concentration of the reactants.
The number of moles is given. No?
Yeah.
So we don't know the volume.
Volume is not given. Oh, it's like you're not given the equilibrium constant also. So you can actually figure this out like purely through stoichiometry only, using the logic. You can figure this out based on stoichiometry. Okay, how's it going?
I don't know.
No? Okay. So initially you've taken these many moles of NO, these many moles of Br2, and nothing of this is formed. At equilibrium, you found that 0.0518 moles of NOBr is formed. So based on stoichiometry, if you had to form these many moles of NOBr, how many moles of NO should have reacted?
Come again.
See, to form 2 moles of NOBr, you need 2 moles of NO. So if you formed 0.0518 moles of NOBr, how many moles of NO are required?
0.0887.
0.0? नहीं, इतना तुमने शुरुआत में लिया. You don't know how much has reacted. That's what you're trying to find out. इसमें से you could have taken
But
excess
we have
also, right?
2 NOBr now, so it means both of the NO are used.
Huh, so this is your stoichiometric equation. Like if you took 2 NOBr, you needed 2 NO. That means that if you formed this much NOBr, how much of this would have been used? अगर 2 मोल चाहिए तो इसका 2 मोल यूज करना पड़ेगा. If you want 4 NOBr,
0.043.5. But I mean half of 0.087.
no, forget about 0.087. Right now, you know that this much NOBr has been formed. Matlab, how much NO has been used up in order to form this much?
X amount of NO.
Yeah, what is X? You guys have done these kind of questions earlier, you guys.
No, Mummy, school we have not.
First chapter mein when we are doing stoichiometry, it's that kind of problem. See, like let me take a different equation, okay? Let's take something you're familiar with. 2H2 plus O2 gives 2H2O. Now, forget about oxygen for now. If I take 2 moles of H2 and unlimited oxygen, how much water will be formed? Hmm?
2 mole.
How many moles?
2.
2, right? If I take 4 moles of H2O, unlimited oxygen again, how much H2O will be formed?
4.
4. Like this ratio is always constant. 2 is to 1 is to 2. I took unlimited, like whatever, some amount of hydrogen, some amount of oxygen. I found that I have 8 moles of H2O. That means how much of hydrogen was used up?
8.
8, right? So basically this ratio is always the same. Agar itna paya, it means that this much has been used up. If I have 8 moles of water, how many moles of oxygen was used up?
4.
4, because for every 2 moles I want 1 mole. So agar 8 mole create hua, to half of 8, so 4 moles, right? So same concept. I took whatever amount. I saw that 0.0518 is formed here. that means how much of NO was used up? Hmm?
Ma'am, just like you told, 2 mole, 2 is to 1 is to 2.
Yeah.
So, so we have 2 moles of NOBr and
Hmm.
2 moles of NO2, NO.
Hmm.
And so NOBr, the value is given 0.518
Hmm.
and NO, the value is given 0.87.
Again, this is
So
the
it's
initial.
0.087.
See, initially you took 0.087. इसमें से कुछ NO react हुआ. That's what we don't know how much has reacted. That's what we have to find out. But you know that after some time, you got this much of NOBr. It means that out of 0.087, how much has reacted?
Zero point zero eight seven minus x.
X को छोड़ दो ना. Forget about this. Let me erase this question mark. That's what we're trying to fill here. At equilibrium, ठीक है. इतना concentration has formed. So how much of NO was, see, in order to get 2 moles, you need 2 moles of NO. In order to get 0.0518, how much of NO do you require? For 2 moles, you need 2. If you want 4 moles, you need 4. If you want 5 moles, you need 5 moles here. If you want 0.0518, how much do you need here? Yeah, Mayas?
0.05.
Exactly. So at the end, if we got this much of NOBr, it means that this much has reacted. And how much of Br2 has reacted following the same logic?
Half of 0.05.
Correct, half of this much. So that would be what? 0.0. So this divided by 2, right? So 2 2s are 4, 1 1. So 2 5s are 10, 1 8, 2 5 9. Okay. तो initially इतना लिया तुमने, उसमें से this much has reacted. So how much is left in the reaction vessel?
The difference.
Difference. Subtract both of them, you'll get it. Yeah. Check how much is it. 2. ये carry over
What do
हो.
we fill in the reacted wala NOBr के नीचे?
We like this don't again, NOBr is not going to react. That's a product formed, right? So it won't be applicable over here.
We don't write anything.
Don't write anything. Yeah. So ये 6 हो गया. So be 3, 0.0352. Similarly, how much of Br2 is left means subtract both of these. 8. So this would be 2, carry overs would be 7. So it become 3, 1. Okay. So final composition is we'll have this much of NO in the reaction vessel, M9, so these many moles of Br2 and 0.0518 moles of NOBr. ठीक है, समझ में आया वाला question?
This is the question is over.
Yeah, that's what you're supposed to find out. Find the composition, matlab, what is the equilibrium mixture composed of? So equilibrium mixture में what all are there?
They just taught us one kind of question for these KC wala part. Ki they gave us a reaction, and to max they give us the values of the concentration of all, and they asked us to find KC.
So that's like the simplest direct question. So at equilibrium, if you know the different concentrations, you can just apply the formula and find out. That is one
So
type
these
of problem.
types of questions would also be asked in our 11th grade.
Yeah. Again, this is more of a stoichiometry based question. Like pehle chapter mein you guys did reactions, right? Stoichiometry calculations. So another way of phrasing this question would be initially these many moles and these many moles of NO and Br are taken. After some time, after the reaction has happened, it was found that you had these many moles of NOBr. So find what is the reaction composition, like what is there in the, how much of NO and Br2 are left in the reaction mixture. That's another way to put it. So basically after some time, this much NOBr is there means based on stoichiometry, you can figure that to produce these many moles of NOBr, based on this ratio, you can figure out how many moles of NO were used, how many moles of Br2 are used. So from that, you can figure out how much is left over. So if you're given the volume of the reaction vessel, you can, using the volume, you can figure out the concentration and find Kc of this particular equilibrium also. That's like one step further. So if it, like, if you're asked to find Kc, then you will, like, this question will be like for a total of 3 marks. Slightly lengthier version. That way. Yeah. What I'll do is I'll compile a bunch of reactions. I'll take it right from level 1 to level 2, level 3 tak. From the simplest direct questions to the slightly more complicated kind of questions. Do it over the weekend, okay? So next class is on Tuesday. We'll start with ionic equilibrium, but do not forget these concepts by the time. I'll send you guys questions for practice.
Okay, ma'am.
Okay.
Okay,
And in
ma'am.
case, yeah, in case you get stuck at any particular question, you can ask me or you can ask on the group. Preferably ask on the group so that others can also chip in. But yeah.
Okay, ma'am.
Okay. Cool.
Thank you.
Sure. No problem.